Okay. There's really no hard and fast rule. Obviously, when you want to calibrate over a range, you want to sample over that range of variability. So if you want a model to work, let's say, during winter and summer months, I mean, if you want to predict long range, when you're doing a climate change study and you're interested in doing something long range, if you just calibrate it to 6 months, obviously that's not long range. So you can't wait for 100 years to calibrate. You may not have that data, but at least 20, 30 years worth of data would capture the variability that's there. So you have to look at the system and say, what is that that I'm trying to model, and do I have enough data? The second part of calibration is that data points, more than the number of data points, the key assumption there is each data should be technically independent of each other. Okay? So if I take a sample today and then I go and take a sample tomorrow, especially in groundwater systems which are very slow to respond, you're pretty much sampling. It's just a replicate sample. You will see some variability, but that variability is not because time has passed and something has changed. It's just showing you the local short-term variability. So samples tend to be autocorrelated if they are too close to each other, or if they are sampled too close in time. So you have to make sure that it's not just the number of samples. You may say I have 1,000 samples, but if they're all sampled in 1 second intervals, you literally don't have 1,000 samples. That's equivalent to having 2 or 3 samples. So there's a concept known as effective sample size, and that effective sample size should be large. Okay, it should be certainly larger than the number of calibration parameters you want to calibrate. In general, the rule is you want to keep your number of regardless of how much data you have, you want to keep your calibration parameters to a minimum. So you don't want to just keep on adding calibration parameters just because you can, because the optimization problem that's used to solve that calibration becomes highly nonlinear, and then you're giving it too many degrees of freedom, which means you will not get a unique solution. So there could be one set of parameters that will give you a statistic, another set of parameters can give you the same set of statistics. So that's called non-uniqueness of calibration. So when we calibrate groundwater models or any environmental models, as a matter of fact, they are never unique. The calibration is not unique. So one approach that's seeing a lot of attention in recent times is to do the calibration, to do multiple calibrations. So instead of doing and saying we did one calibration and this is what it is, we make multiple calibrations, and then we average over those models. So a lot of times we use Bayesian approaches to do that averaging, because we can say that we actually believe in this model a little bit more than we believe in this model versus this model. So, but the net result, we don't know. All of these models are, there's uncertainty associated with each of these models, and based on that we can average it. Of course, some models have greater uncertainty, so they have to be weighed lower, and some models have less uncertainty, which means they get greater weights. So we take all that and do weighting. That's very common in climate models. You get multiple models, you do what are called ensemble models. The other way, if you're making forecasts, you use the same technique and you say, okay, I'll fit one model, second model, third model, fourth model, but I know that in this range this model does good, in this range this model does good, in this range this model does good. So you create an ensemble of a model which is multiple models put together, and depending on what your input is, you pick the relevant model and make a forecast. So ensemble forecasts generally are better than single model forecasts. Even though you may have some terribly wrong models, they over the long run tend to outperform any single model, because the variability, they're just better because they can capture the variability better and they get weighted accordingly. So long answer to your short question, so the short answer is the more number of points you have, the better it is, but it should be enough to capture the variability. The more data points you have, the calibration will not be that good because you're trying to calibrate over much larger variability. So at a minimum, you need, if you have n parameters, you need to have at least n data points, n, whatever that n is, like, so otherwise calibration is like solving a system of equations. So if you don't have, if you have 5 unknowns, you should at least have 5 equations, right? So have 5 data points. If you have 15 or 20, we can still solve that in some regression sense, but if it's only like 3, then you have a highly non-unique solution, like, so you can't solve it. You have to, it's an underdetermined system as opposed to an overdetermined system. So looks like we are in business. So let me complete the gradient calculations that we were doing. This is again in your textbook. So if we want to calculate hydraulic gradient, in your notes I show you one way to do it. That's based off of how finite element models are done and how, like, interpolation is done. But in general, we don't know we don't know the direction of our groundwater flow. Okay? In surface water systems, we know what it is, but in groundwater, we can't tell because we can't see it. So what we do is, at a minimum, you need 3 wells, okay? And we connect these wells. So I'm going to call it well 1, well 2, well 3. And at each well, we need to calculate the hydraulic head. And the hydraulic head is gamma plus z. Okay? So if I have, that's my datum, and this is my bedrock, okay, and here's my well. Okay. It's screened to some degree here, and you have to take a common datum to make your calculations. Generally, you will stand here, and there is a water table somewhere, and you'll measure this depth. This is what we call depth to water table. Okay? But you may have another well here, and its depth to water table may be a little different because the land surface is undulated. There is some plane to that land surface. So you can never make your land surface, what we call LSD or land surface datum, to be your datum for calculating hydraulic heads. Typically we use mean sea level because that's kind of a standard datum. And then from the mean sea level all the way to the screening, like, so if you have a well that's screened, we typically go to about half the screen length, and we call that Z1. And then from there to this is our P1 over gamma term. Okay? Gamma is the specific weight, that's your pressure. So the water level that you measured from the screen all the way to the top is your pressure head, and to the screen from the datum is your elevation head. Okay? So our total head H1 is P1 over gamma plus Z1. Okay? So the way we typically do water level measurements are we have a tape. The crudest way to do it is to take a regular steel tape, put chalk on it, and drop that steel tape, and then pull it out. Where it hits the water, the chalk disappears, it melts into the water, and then the remaining portion, the chalk is left, so you pull out, and it'll say, okay, this is where the measurement was made. Somewhat crude, highly error prone, so the better way to do it is to use a water level meter. And what that water level meter does is, it's a very simple contraption. It's still a tape. You can roll it down, but it's got like 2 electrodes, and it's usually connected either to a bulb or to some sounding device. so that when it hits the water, the circuit is complete and it will give you the water. Okay? The new advancements are to use pressure transducers. So let me just show you. So those are like very typical water level meters. This has got a probe, and you drop the probe into the well, and when the circuit is complete, you measure the length on the tape. It's good to about a few centimeters. So like, you can measure water levels to an accuracy of about 1 centimeter or so. Like, so the other way to do it is to use water loggers. There are two types of water loggers. This is what's called as a vented water logger. And what this is, it's got a pressure transducer here, and it's got a pipe that vents to the atmosphere. So what we do is we place this logger in the field, and then what it measures is the pressure of the water column that it experiences. Okay? So if I drop it here, and this happens to be where my water column is, I want to calculate HW. What I calculate is this distance, which I know, like, because you usually know your elevation from the mean sea level, and you also know this distance because you know where you put that transducer, where you put that logger, like, where you dropped it to, and this measures this distance. Okay. So in essence, you go from here to here, and then you subtract that length till you get back here, and then you add that P over gamma term, you get here, and that becomes your pressure. The advantage is this is open to atmosphere, which means what you're measuring is gauge pressure. Okay. You don't have to correct for barometric changes that take place or the pressure differences that take place. The downside of this is you have to leave a pipe open. This pipe, this thing is left open at the well because it has to vent to that atmosphere, like, so it has to go up, and that's sometimes error prone. Like, so I've lost a lot of these because we would put it in the field in the wells, and then some animal would go and chew it, and you would start seeing some funky readings that you're not supposed to see, like, so but 10, 15, 10, 12 years ago, this was the technology. This was the only way you could measure if you wanted to measure automatically. The good news is you can connect this to a computer. There's usually a little chip inside, and you can take measurements as low as 1/10 of a second to about a second accuracy. Like, so you can take measurements almost every 1/10 of a second, and very reliably at 1 second intervals. Like, so if you want to know what is the short-term fluctuation, it's a lot easier to do this because you can collect data at every second. You will see some noise, but the data will be very close to each other. On the other hand, if you let it run for a day, you will usually see that it goes up and goes down depending on how the well is being pumped or how nearby wells are being pumped, and so on and so forth. The latest tool is to use what are called as a vented transducer, a non-vented transducer. So this is what it looks like. You can actually put it in your hand, so it's about the size of the palm of your hand. And the same principle, you drop it, and it measures the pressure that of the water that it encounters. So you need to make sure that when you drop this, you don't drop it here because it will just measure atmospheric pressure. Like, so you have to drop it where the water level is. And if you expect your water table to go up and down, you need to make sure that this is below the lowest water level it can encounter. If it drops here, it will not measure anything, like, because it has no pressure to measure. The only difference is this is not open to atmosphere. So what it's measuring is not just the pressure that's exerted by this water, but it's also measuring the pressure that's exerted by the air on top of it, okay, which is your atmospheric pressure. So it measures the absolute pressure and not the gauge pressure, which means if I want to get it in gauge pressure, I have to subtract out my absolute pressure. You will actually get a very similar sensor that you put on top of this well, and that measures the barometric pressure or the change in the atmospheric pressure. So you subtract that from the total pressure that's being measured here, and you'll get the gauge pressure. Okay, so the downside is at a site you don't have to put a barologger or a barometric pressure measurement at every well, because the barometric pressure doesn't change much spatially, unless of course one of your sample is at the sea level and the other one happens to be on top of a mountain. Of course, you will see some barometric variations, but generally the field is a few feet undulations, like tens of feet of undulation. Your barometric pressure doesn't change as much, so you need to make at least one barometric pressure reading, and you can put many of these, so much more convenient because they're much smaller and they're completely in the well, so we can close the well and go, and that so the instrument is protected. They tend to run about $1,200 to $1,500 per sampler. So if you're monitoring 20, 30 wells, the price goes up fairly quickly. You're talking about $30,000, $50,000 worth of monitoring instrument. Again, you can program this. What you do is you pull it out, and you can actually unscrew this cap. And if you unscrew this cap, it has a USB type attachment that you can put it into your computer, and it will download all the data that we have. There are some places where we can actually take that USB attachment and connect it to a wire and put it to a router and remotely capture this data if we have telemetry to do that. So we need to somehow read this, give it an IP address and read it, and you can get it on the computer. You can sit at your work and look at it. Of course, that has its pluses and minuses, so especially when a lot of these wells tend to be at remote sites. You may not get good internet connection, so it may or may not work, but there are sites where we have tried it, and it works just fine. If you have good internet connection, if you have good broadband connection, we can actually pull that data out without having to leave the site. So once every few months we go and delete all the files that's on the machine, and make a manual backup, and then reset it, and it'll start all over again. So if you want continuous monitoring where we can't have gaps, on some projects they won't allow us to have gaps. We put 2 of these, and when we pull out one, the other one's still recording, and then we put this back there and pull the other one out, and that's recording. So we never lose, we never miss a beat, if so to speak. So when we calculate that data, so those are some of the technologies that we use to calculate hydraulic heads. Very common to put these in contaminated sites because we need the data. So if you have hydraulic head data, such as the one I'm showing here, we can use R to make these calculations. So what I show here is my X coordinates and Y coordinates. These are just some local coordinates that we fixed. When you do these calculations, GPS, we can use GPS to get these measurements. Typically GPS measures what? The position. What are the common units in which you get position? So you measure the latitude and the longitude. What are latitude and longitude? Way back to your 5th grade geography or 6th grade geography, where you were first exposed to these terms. What do they stand for? Right. So latitude measures what? Correct. So measures the angles between the equator and the poles, and then the other one measures to the equator, one measures to the pole, basically, like, so you have parallel, they look parallel lines, but necessarily they're not parallel because they do connect at the poles. And it also means that if I take the difference between two latitudes, the distance is actually different at different parts of the earth. Okay. The good advantage is earth is a geoid, so two angles will give you a very accurate position of where you are, but the two angles, if I take the difference between two angles, the distance is not necessarily the same every place in the world. Okay, so near the poles it could be very close to zero, and it will have the maximal distance near the equator. So India, we are somewhere close to the equator, so we'll have some errors, but better than doing this in the US, which is a little bit further away from the equator. So so we usually bring it down to a projected coordinate system. A projected coordinate system basically is takes two angles, flattens it out. So when you take a three-dimensional object and flatten it out to two-dimensional space, something has to give. So what do you want to give? You have to give up something because you can't put a 3D on a 2D. So you have to either give up the shape or how it looks, or you have to give up the distance measures. So you can preserve how it looks, but your distances will not be correct because you have a distorted image, like on a two-dimensional space. Or you can preserve the distances correct, but the image will be distorted. So one of them has to happen. Okay. If you're making a map to show something, it's always good to preserve shape and distort your areas because it's just a visualization part. On the other hand, if you're making calculations, you want to select a projection system that keeps the areas and the lengths constant as opposed to the shape. Usually it ends up twisting things, like, so don't ever put, so Albers equal area projection, is a very common projection system where you preserve the area but not the shape. If you just plot it in lat longs or like in geographic coordinate systems, it'll look nice. It'll give you the shape, but the distances are not preserved. Like, so those are two common things. There is also something known as the UTM projection or the Universal Transverse Mercator. What it does is it locally changes your coordinate system so that it preserves the shape, and it does its best to preserve the area. Like, so it kind of gives up a little bit of this, a little bit of that, so that net result is you have errors in both shape and distances, but they are somewhat manageable, at least for engineering purposes. So which is why UTM was done. Especially if you live in Bengal and you plot it in Albers equal area or some distorted measures, some of your points may show up what would be Bangladesh or in the ocean. So if you show that map to somebody, they'll be like upset or say you're wrong because it's in the ocean or it's somewhere else. So so when you put it in GCS or the geographic coordinate system, it looks fine, but when you make the calculations, use a projected coordinate system that preserves area. So we have these measurements, x and y, some local coordinate systems. LSD is the land surface datum, and it's being measured from mean sea level. All of these are in feet because that's what we use in the US. So it's showing that the elevation or the land surface elevation changes a little bit. The depth to water table is measured. So this is me standing at the elevation and measuring the depth to water table, and that's given as these numbers. So I can calculate the hydraulic head simply by taking this and subtracting this number out. Okay, and so I have 3 hydraulic head measurements. How do I go about calculating the gradient? So in your notes, I show you a calculation that's based on, basically what we want to do is fit an equation for a plane one way or the other. Like, so there are a couple of ways of doing it. I show one way in your book. The other way to do it is to simply write an equation h equals ax plus by plus d, and then the derivative of is a, which is that coefficient, and then which is that coefficient. Okay. So in R you can do this using a function that's available called lm function. So if I open up R, and so okay. So I'm going to go File, Open New Script, and so first thing is to read the data, and my x coordinates are 5, 30, and 80. So I'm going to go and, well, let me do it this way. I'm going to go open Excel. And I'm going to put my x coordinates, y coordinate, and h, because I'm pretty sure all of you can do addition and subtraction. So it's 5, 30, and 80. And this is 12, 50, and 30. And my hydraulic heads are 2312.8, then 2311.44, 2312.42, okay. And I'm going to save this. Browse. Go to my Dropbox. Groundwater again. Make a new folder. Call it gradient. And I'm saving my heads. I'm going to save it as a CSV file or a comma separated file. You can actually read Excel files into R, but you need a package to do that. R tends to not do anything that's commercial in its base package. So because it's completely free, it wants to keep it completely free. You can open a CSV file in a notepad. Typically by default we open it in Excel because most people have it, but R is written with the philosophy that even if you don't have this software, you should still be able to run it. So it kind of keeps it. So then we close it. I'll go back to R. And I will set my working directory. And what's my working directory? There. So the best way to do it is to copy it from Windows Explorer, go back and put double backslashes to make sure, and just to make sure it runs, I'll run it, and it ran. And then the next step for me is to read that file, and I can do that using read.csv file. And I call the files heads, and header equals true. So the first row is a header row, like it's got names of the columns. So we put header equals true. Always make this true capital T, or write it as TRUE with a capital T. Otherwise, it won't, R won't recognize it. So if I run this, and then if I open A on the console, it shows me that I have X, Y, and H. Okay. So when I say read.csv, it brings in as what is called as a data frame. A data frame simply is, it's got columns of data, and one good thing about a data frame is you can bring in data of different types. So you could have data in integers, you could have data in real numbers, you could have data as factors, like which are A, B, C, D, E, F, like text, string. So you can bring data of multiple formats all into one using this read.csv file. Read.csv is a wrapper function for what's called as a read.table. Read.table can be used if you have, instead of comma separated files, if you have tab or space or something else separated files, you use read.table and tell what the separator is but read.csv makes it a lot easier. So if you're creating your data and taking your data, I would say use read.csv because it's just convenient, provides a convenient wrapper. Okay. So the next step for us is to get the data. We'll just extract the data. There are two ways to, so once it comes in as A, we are storing all the data that's in this file in this object called A, and A will have all these things. So I can go and assign each column and pull this out. Okay. There is something you can do, which I recommend that you not ever do, is if I do attach A, what it does is it pulls out X and makes a variable, Y a variable, and an H a variable, and puts all the data for you. So it kind of separates it out. Okay. I recommend that you not do it, because if you reuse that variable again, it will just overwrite it and it will not tell you. Okay. So sometimes if you say you bring in another CSV file and that also has H, it will just mask the H in the first one and then rewrite it on top of it. So it creates a lot more headaches than it helps in the long run. So I strongly dissuade you from using attach A. So you can actually attach A and do what's called as a detach A, which will remove that, but sometimes it doesn't quite remove it. So generally we don't want to do it. X is equal to, you can always access those using the $sign. So you can use A.x will give me X, Y will be $Y, and then H is $H. Okay. And then perform regression, and basically I'm going to store it in some object called grad, and say I use LM, which is the linear model, and I want my y is H. Okay. And instead of equal to, you put tilde, which is that squiggly line, and then I want X plus Y. If you don't put anything, by default it will put an intercept for you. Here the intercept has no meaning other than it's just a datum of some sort. And if I run this, and I go and put grad, it will give me the intercept, the slope in the X and Y direction. Okay. So this is the gradient in the X direction, this is the gradient in the Y direction. Okay. Which means the numbers are what? 4.183 times 10 to the negative 3. So if I choose X going positive this way, Y going positive that way, Y will go negative in this direction, and x will go negative in this direction. Okay, so I can, those are vectors. So I have 4.183 times 10 to the negative 3, that's 0.004, going in the positive direction. So that would be 0.0048 or whatever, right? 418, okay, or 42. Okay. And the next one is minus 3.85 times 10 to the negative 2. So it's an order of magnitude higher, but it's negative. So this is this, and this is minus 0.3 point, how much is it? 0.0385. Okay. So that's my gradient in this direction. That's my gradient in that direction. What's my resultant gradient? Which direction? So I make my vectors arrows meet, and that will be the direction of my gradient, and the value will be equal to G resultant is equal to, by Pythagorean theorem, del H over del X squared plus del H over del Y squared, right? And then the angle tan inverse is a tan inverse or tan of theta is, and the inverse tan of it will give you that value, right? So what's the direction of the groundwater flow? So this is north, east, south, west, southeast. Right, so it's the negative part, so it's a mirror image onto the other side. It's not perpendicular to your gradient, it's just the negative sign, so your flow will be, your groundwater is moving in that direction because you have a minus, okay, because our Darcy's law says that Q equals minus K del H over del R, whatever the resultant del is. So if you get the gradient, always don't forget that negative sign, your flow has to go in that direction. And one line of code will give you what those gradients are. If you have more than, let's say you have 5 wells or 6 wells, you can still apply this method, but the method I show you in the textbook only works for 3 wells. So because it does like splice interpolation between the 3 wells, like that's the formula for it. So you have to pick 3 wells for the outermost 3 wells and then use that formula that I give you, or you can use the LM function and get the gradients. So that's how we get gradient. The next thing we need to get to apply Darcy's law is to get hydraulic conductivity. How do we get hydraulic conductivity? So one approach, a lot of times if you don't have hydraulic conductivity, is to just go to a chart like this and get what the hydraulic conductivity is, like get an estimate for that hydraulic conductivity. What you will typically see is that hydraulic conductivity varies over several orders of magnitude for a given soil type, for a given aquifer material. So which number will you pick? Because if you want to set up a model, you can't give it a range, you have to give one hydraulic conductivity. So what is that hydraulic conductivity that you're going to pick? What's that? 315? Oh, D50? I don't have grain size, I just have an estimate of hydraulic conductivity. So these are reported hydraulic conductivity values at. You can calibrate over the range. For that you need outputs, so you will need heads and stuff, and calibration generally is a highly non-unique problem. Even to run calibration you have to start with some good starting condition. If you start with a very bad condition, you will end up calibrating to a bad number, like it won't converge to a good number. So you still have to get a good estimate. Okay, so if I have range that goes over orders of magnitude and I want one number, what would be a good number? Mid value, that's one thing. What else? What type of a mean would you prefer? Mode will be the mid value. I want some sort of a mean value. Will the mean and the mode be the same? They will be on a log scale, not necessarily on linear scale, because you're talking about orders of magnitude, right? So typically we use a geometric mean because the range of variability is better characterized instead of arithmetic mean. If you do arithmetic mean, you will always overestimate hydraulic. You will be on the higher end of the hydraulic conductivity rather than on the lower end. So if you have a range like this, you would randomly pick data points from that range and take a geometric mean and say that's my best guess based on geology. Okay? So that would be the crudest way. So if you're doing very preliminary modeling, like modeling just to get an idea of what is going to happen, you will have 3 wells at a contaminated site, and you will say based on that this is the direction of the flow. You will have some geology, it will tell you whether it's sand, silt or clay or some sort, and based on that you could go to a chart like this and get a very crude estimate of what the hydraulic conductivity is, and based on that say, well, my flow is going to, my Darcy's law or my Darcy flux is going to be this much. If I divide that by the porosity, I get the average linear velocity like we talked yesterday, and using that average linear velocity, you can calculate and say how long will it take for a pollutant to move from point A to point B. Okay. So I calculate gradient from 3 wells, I get some geology, based on the geology I get an estimate for hydraulic conductivity. Based on that estimate of hydraulic conductivity, I multiply that with the gradient, divide by the porosity. What porosity, what values, where do you get values of porosity? What's a typical porosity for sand? Sand and gravels are usual aquifers. What number would you use for porosity? Point how much? 0.35, 30%, 0.3, 0.35. Anybody else going up or down? So 0.25, 0.3 is a typical number. So we have something called the total porosity, which is the volume of voids divided by the volume total. That's your porosity. We talked about it. When we do, some of that pores may not be connected to each other. So if you don't have pores that are connected to each other, then the water will just go flow into the pore and it will never come out. So at total porosity for sand is somewhere about 0.4, 0.45. But when we do modeling, we are not interested in dead end pores, pores that dead end. So we want to get an estimate of what is the interconnected pores, and that's very hard to do. By and large, we make an assumption of 0.25 or 0.3 in that range, that's called effective porosity. Of course, the porosity is showing up in the denominator, which means if I make that number smaller, your velocity will be higher. Okay? And if I make that number larger, your velocity will be lower. Okay? So if you have to be wrong, which you are because you're doing all kinds of estimations, would you rather have a higher velocity or a lower velocity? Right? So the question I'm asking is, here is a contaminated site. Okay, here is a well. Okay, this well is, let's say, 200 meters from the site. Okay, I got my gradient. Okay, some gradient. Okay, I got my hydraulic conductivity. It's a sand, so I'll go to clean sands. This is in meters per day, so let's pick it's somewhere between 0.5 to 1,000 meters per day. So my K is square root of 0.5 times 1,000. Okay, whatever that number is. Okay, how much? That's square root of 5,000 is 70.71. Okay, let's call it 71. It's all crude meters per day, right? And okay, let's first get Q, which is, and of course there's a negative sign to it. So negative 71 times 0.001, that's equal to how much? 0.07 meters per day. So this is the flux of water, like, you know, this is averaged over both the pores and the solid grains, right? So now I want to divide it by porosity. My V is equal to Q over N. What's my value of N? Someone said 0.3, someone said 0.25. Let's have two estimates. So if I take that 0.07 meters per day divided by 0.3, I get how much? (0.23). Okay, and if I divide it by meters per day, that's my velocity 1 estimate. Velocity 2 estimate is 0.07 divided by 0.25. 0.3, 0.28. My distance is 200 meters. So in the first case, it will take how many years? How many days? 200 divided by, this is my travel time. 200 divided by 0.23 is 870. So 200 divided by 0.28, 714. Okay. So both these numbers are just estimates for what they are, right? I mean, we don't know what the true porosity is. We don't know what the true hydraulic conductivity is. But just based on, we don't even know what the true gradient is. We've just made one measurement and got these values. But at least, you know, in one case, you're saying it takes about 870 days. In another case, you say that it takes about 700 days. Which estimate would you go with? 714? Why? It takes less time to get here, so you're saying, okay, you know, it's going to get there sooner than later, so we're going to do that. What's the downside of doing that? The downside of doing that is if the velocity is high, the mixing associated with it is also high. Okay. If I take a spoon and stir it very slowly, I'll have less mixing. If I stir it very fast, I'll have more mixing. Okay. So what happens? There'll be the concentration of the contaminant is going to go down because now it's a better mix than it was. Okay. So on one hand, yes, if you're trying to estimate the travel time, and you say I want a higher velocity, that's good, but the second part of the picture is it's not just any level of contaminant that's going to cause a problem. There is a certain threshold that causes a problem. If something dilutes it, like mixing wood, then that actually makes the estimate less conservative. So you have to look at both sides before you pick which one you want. But generally, you would say, based on our best guess, it's somewhere between 700 to 800 days, and I'll work from there. So how can we get hydraulic conductivity? Okay, obviously our uncertainty is in that hydraulic conductivity measurement and then in the porosity measurement. So how can we measure this in the field? Anybody? So traditionally we do what's called as a pumping test. Okay, what does pumping test do? We pump at a well, and then we have an observation well, and we see what the drawdown looks like. And based on how the drawdown looks like, we use the radial groundwater flow equation, which is also called the tie solution in confined aquifers, or a similar type of solution in the Huntus-Jacob solution in leaky aquifers, or Bolton or Neumann. There is a bunch of methods in unconfined aquifers, and we try to estimate that hydraulic conductivity. At contaminated sites, the problem is if you pump water, you're pumping contaminated water. So you have to do something with that water. You can't just pump and dispose it off. So a key challenge to pumping tests is, what do you do with the water that you're pumping? Okay. When you put municipal wells, or wells for like municipal water supply or irrigation water supply, you want large quantities of water, like thousands of cubic meters per day, like hundreds of cubic meters per day, and you want to do a pumping test because you're drawing large amount of water into the system. When you are at a contaminated site, you really don't want to pump that much amount of water because you will be pumping out a lot of contaminated water, and you don't know what to do with it. Okay, so most places we don't do pumping tests. Instead, we do what are called slug tests. Okay, a slug test simply is a test where we go and take a well, okay, and so we have a well. It's screened somewhere. This is our land surface, and usually, as I said, there is some gravel pack associated with that well, and the water table is somewhere here. Okay. So we know our initial water table depth, okay, and we can also get it from some datum if you want. Okay. What we do is either we put a weight, some weight, okay, into this well. So we introduce some known weight into this well. And the simplest way to do it is to basically take a baler where you're getting water sample, just pour water in it, and then quickly release that into the well. Okay. What happens if I put this weight is the water level will rise, right, because of buoyancy. The water will just go up, and the volume of water that's displaced is equal to the weight of slug that you put in, according to who? Archimedes principle, right? So locally, in the aquifer, the water is here. In the well, the water is here. Okay. So essentially, there is a hydraulic gradient created because the water here is at a higher head and the water here is at a lower head. Water will start moving out of the aquifer, okay, and come back to this position in the well. It will re-equilibrate back. Okay. So this drops at a certain rate, right? That rate is the rate at which water is leaving my well and getting into the aquifer, and then moving out of the aquifer. Okay. So essentially by measuring the rate at which this drop takes place, I should get an estimate of what the hydraulic conduct, how easily the water is flowing in this. Okay? So that's what is typically called as a test where we are actually introducing the weight. This is a slug test. This is called a slug. Okay. Then when the water level comes back to its original level, we will remove the slug. Okay. When we remove the slug, artificially the water gets depressed because that buoyancy or the effect of that weight is gone. So the water level will now drop. Okay. Locally, the water level is here in the well. The water level is here in the aquifer. So water will start flowing back into the aquifer, and this water level will raise back. And the rate at which the water is coming into the well is proportional to the hydraulic conductivity of that well. So that's what slug tests do. Is the idea behind slug tests is you put a weight, locally change the elevation either up or down in that well, and based on that you try to figure out what is the rate at which water does. What is the good news about this at contaminated sites? The good news is we're not pulling out any water. All we have to do is make sure that the slug is of course exposed to some contaminated water in the well, so we have to dispose that slug out properly. But other than that, there is very minimal contact to us with the groundwater. As a matter of fact, a lot of times we use a sampler or a baler that we use to collect samples, fill it with water and just use that as a slug, because once we get the sample, we are going to dispose of that baler anyways, so it makes it a lot easier. So what is the benefit of this versus a pump test, and what's the disadvantage of this method over a pump test? Okay, in a pump test, what we do is we have the same situation, but we have a well. We actually pump water, and as we pump water, the drawdown the water will start coming to the well, and you start creating this drawdown. You also have an observation well, and you will see that corner depression over time come into this well as well. Okay? And usually make the measurements of drawdown at the observation well, use tight solution, and back out your hydraulic conductivity. You don't want to do that at this well because you're pumping this well, so the water is sloshing, and so because your pump is producing a lot of energy that not all of which is being used to pump the water up. Some of it is used to generate heat or loss due to friction. So the water will be moving quite a bit in these wells. Okay, so we generally refrain from taking drawdown measurements here. We usually want to take drawdown measurements at an observation well. Sometimes we may not have an observation well, in which case we resort and we do what's called as a single well pumping test, where there is only one well and we pump it and we get both. The downside of a single well pumping test is there are two parameters that we want to measure. One is K, one is S. K is your hydraulic conductivity, S is your storage. You will not get storage value if you do a single well test. As a matter of fact, you will not get storage value even from a slug test. You can only get hydraulic conductivity. Okay. So if you want storage values or storage coefficient values, you have to have an observation well and do a pump test. Usually the storage is not a problem for us. It is a big issue when it comes to water supply, or putting a well that's needed for water supply. But at contaminated sites, we're not trying to pump that water to see what's happening. So what we are more interested in is how easily is the water moving, how fast will that plume move, and what do I need to do to contain that plume. So those are our questions. So because of that questions, the storage coefficient is not of importance to us. But doing a pump test at a contaminated site gives us a lot of water, and under RCRA, at least in the US, whoever pumps that water becomes responsible for that contamination. So they have to somehow dispose it off. So companies that do this pumping tests don't want to take that responsibility. So they resort to slug tests. The hydraulic conductivity, as I said yesterday, was an average value, right? It's averaged over what distance? Here, this pump test, the water has this cone of influence. So my hydraulic conductivity that I'm getting is a measure of how easily the water can flow in that little cone of influence. Whereas if I do a pump test, this is my influence, okay, cone of influence. So my hydraulic conductivity K will be a function of, it's an average over that larger area. Okay. So generally speaking, the farther away I move this well, observation well, the larger will be my hydraulic conductivity. Okay. That's what's called as a scale dependency. Why? Because as I make my radius of influence larger, I'm encountering a variety of different pores. I'm encountering more pores that can actually give water than when I do it over a much smaller range. I get what's called as a local hydraulic conductivity estimate. So slug test, the disadvantage is it will not tell you what the regional flow is. It will just tell you what the flow looks like at that site. And as a matter of fact, we typically do multiple slug tests at multiple wells that we have at a site to see what the local geology, how is the local geology varying. Like, the good news about slug test is you can do a slug test in like 15-20 minutes. Okay? If you want to do a pumping test, you should pump for at least 6, 7, 8 hours at the very, very minimum. A typical pumping test for a water supply project would be a 24, 48, or a 72-hour pump test. Like, so 72-hour pump tests are very, very common when you want to put a large well. If you want to get vertical hydraulic conductivities, you probably will have to do pump tests that runs for weeks. Those are extremely challenging because you have a pump that's running continuously, and the pump will wear out. So your pump will burn out before, because you're just running the pump day in, day out, day in, day out. So you have to occasionally remove the pump and put another pump and have a SCADA system to switch from one pump to another. So those get very complicated. But in general, slug tests, especially with the pressure transducers that we have, doing slug tests has become much, much easier, because one of the difficulties of slug tests was when we put the slug and the water level rises, that water level drops very quickly initially, but as the gradient between the two starts to get lower or becomes zero, the water will move more slowly. If I have a high gradient, the water will move faster, like till these two gradients equilibrate. But if I have a very small gradient, the flow is much smaller, like the flow rate is much smaller, because the hydraulic conductivity is the same, except your gradient now is, the driving force is much smaller. So over time, the first few seconds of that slug test is very important, because that's where most of the water is being lost. And back in the day, we had to manually measure that in the field. So somebody would be taking a measurement and reading it, and somebody would be trying to write down. It used to be very windy, like somebody's page got fluttered, measurements are missed. That's a problem. Okay, then we decided, hey, we've got audio, like we've got tapes. Okay, we're gonna measure it, right? So somebody is going to make the reading and say it out loud, and we capture it on a tape. Winds just are too much when you're out in the field, and all you hear is shh, and then there is no measurements. You have to go redo the slug test again, like slow. So when the transducers came, slug test became a lot easier, like or even pump test became a lot easier. So that's how we get hydraulic conductivity. Why do we need all this information? We need all this information. So I show you how to make calculations under confined and unconfined aquifer conditions in the notes. So take a look at it at your leisure. But let's look at a few other things, which is the transport process. So the first transport process is advection. I talked about flux and loadings. These are concepts that you need to have. So we need to be able to write advective flux and advective loading. So the advective flux is your average linear velocity times the concentration. The advective loading is your flow rate times the concentration. Okay, so Again, in both these units, we are assuming the concentration is written in moles per liter or milligrams per liter. If you write it in some other format, you have to make appropriate corrections for it. Okay. So we use Darcy's law and we calculate our velocities. Okay. So that's the calculation I showed. Again, Darcy's law is average. The Darcy velocity or your specific discharge is averaged over the entire cross section, including pore space and solid matrix, whereas the average linear velocity just takes the average over all the pore space at a given cross section. Individual pore, the velocity is going to be very different, but we seldom need that information. What we need is average over the entire pores at a given cross section. Okay? Because at a well, we have screen, the water that's coming in is averaged over the entire screen. So it really doesn't matter. We cannot make a concentration measurement associated with each flow path or with each pore. So a velocity associated with each pore is rather useless because we can't really say how is that flux varying at a cross section. Okay. So the second phenomenon, that's not the only reason why pollutants move. The second phenomenon which causes pollutant to move is diffusion. Okay? Diffusion is a strictly molecular scale phenomenon. And why do we get diffusion? Concentration gradient. Why do we get a concentration gradient? Because of Brownian motion, like or random. So the molecules are just moving randomly. Okay. If the solute is concentrated, there is more energy to that solute, so the solvent usually is at a much lower energy, because you've got a lot of molecules in it. So the molecules have to stay in orderly fashion because there's not enough molecules to bump against each other. They're constantly colliding, but there are so many molecules that they can't move much, they're just sitting there. On the other hand, the solute has got a lot fewer molecules, so when they bump with each other, they tend to move much farther. They tend to have a lot more energy. Okay, so they're randomly bumping against each other, and because they two bumped, one went away here. Now it doesn't have any solute molecules, so it just stays there. Okay, whereas this may bump with something else and go somewhere. So eventually, molecules are moving randomly at a molecular scale, but if we start looking at a macro scale, they tend to move from regions of higher concentration to lower concentration, because once they get bumped into regions of lower concentrations, there are fewer solid molecules to interact with and then come back to the region of higher concentration. It's not that the molecules don't, they do come back, but the net movement from higher concentration to lower concentration is much higher compared to the movement from the lower concentrations to higher concentration. So there is a net gradient that gets established on a macro scale, just because on a micro scale that the molecules are just moving randomly against each other or colliding randomly against each other. So a molecular diffusion is strictly a chemical phenomenon. Okay. What does it depend on? Temperature. Okay. Temperature and pressure are always good ones. Okay, they'll say every chemical phenomenon will depend on temperature and pressure. Okay, so you will never go wrong if you just say temperature or pressure. Groundwater systems tend to be fairly isothermal, temperatures are whatever the temperatures are, they don't change that much. They do vary a little bit, but they're not as dramatic as surface water systems. Okay, so our temperature is roughly constant. Our pressure is roughly constant. So would all molecules roughly have the same type of diffusion? Do you expect bigger molecules to have less diffusion and smaller molecules to have greater diffusion? Do you think size matters? smaller molecules have greater diffusion? Why? What happens when the molecule is large? Velocity changes. Why does the velocity change? The tendency of molecule to the tendency of the molecule to settle down, gravity starts to play a slightly bigger role. Okay. The other thing is the molecule becomes, because it has more mass, it's a little bit sluggish. Okay. To hit that, if I hit with certain energy a molecule that is small, it will move faster versus one that's slightly larger. I need a little bit more energy to push it out into that domain. So the mass does cause some inertia, and there's also gravity trying to pull things down a little bit. So there could be some settling. Although at that molecular scale, Stokes' law, the gravity is not a very large force. The electrostatic forces are much higher than gravity. Gravity tends to be a much weaker force. Okay, just like with Stokes' law, you will never get 100% settling, right? Because after a certain particle size, things just don't settle that quickly. They just stay afloat. Okay, so that's what happens to molecules. So there is a weak dependency on the molecular weight, but in general, almost all molecules will diffuse. Molecular diffusion is one of those transport phenomena that happens regardless of whether there is flow or not. Okay, so the flow causes advection. Even if the groundwater were to be static, a contaminant will move because of diffusion. Okay. So the way we define it is using what's called as Fick's law, and Fick's law basically says that my concentration loading due to diffusion is a function of concentration gradient, is a function of the area of cross section, and some constant called the coefficient of molecular diffusion. Okay. So it's very similar to Darcy's law, and as a matter of fact, it was stated right around the time when Darcy stated his Darcy's law. So Fick's law basically says that the loading is directly proportional to the concentration loading, or the mass flow rate. Darcy was working with volumetric flow rate. Fick's was working with mass flow rate. The mass flow rate is just mass per time. So the transport of mass per time is directly proportional to the cross-sectional area. So the bigger I make it, the more mass will flow, and then it's proportional to the concentration gradient, which means if I have high concentration here, low concentration here, there will be a lot more movement due to diffusion than when the concentrations are close to each other, when the driving force goes away. Okay. Why is this N here, the porosity term? Because when we are talking about diffusion in water, we are only talking about diffusion in the water phase. Okay, so the porosity basically tells us that our diffusion is only happening in the liquid phase and not happening into the solid phase. So there is no diffusion in the solid phase. There is only diffusion in the liquid phase. To account for that, we put that in. The loading is just loading. If you divide the loading by cross-sectional area, you get the flux, and the flux is proportional to concentration gradient. Flux is proportional to diffusion. It looks very similar in surface water systems, but with the exception of N, which becomes equal to 1. Okay. So the coefficient of molecular diffusion is basically a chemical property. Okay. It has nothing to do with porous media. Okay. If you have Vadose zone, you could have diffusion taking place both in the air phase and diffusion taking place in the liquid phase, because there are two fluids there. Okay. So the gaseous liquid diffusion coefficient, or the DG air here, is what would happen if there was only air, no soil. Okay. Liquid diffusion coefficient is the diffusion that would take place if the entire system was liquid and there was no soil. Okay. But there is solids, there is air, there is liquids. So the air and liquids are connected in some tortuous path in the Vadar zone, and because of that, we correct for the moisture content and the porosity. So we kind of look and say, how much of that Vadar zone is occupied by my air content, how much of it is occupied by moisture content. And Millington Quirk, they gave out this nonlinear relationship, and it says that it has a slightly bigger dependence to the moisture content than the total porosity, and you can calculate the gaseous and the liquid diffusion coefficients in soils because of the presence of soil. It is modified, the fact that it's only in pores. Okay. So if you go to that website that I'm showing there, they have a database of all common contaminants and the liquid diffusion coefficients for those contaminants. You can actually calculate them using molecular thermodynamic principles, something called QSARs. So you can look at the bond structures of organic compounds, and then from there back out what the liquid diffusion coefficient will be like. So there are ways to do it, but generally you will go to a database and get that values. Very rarely will we measure this in the lab. Dispersion. Now, what's dispersion? So what's happening is, I have a flow path, I have another flow path, okay. So one is a short path, one is a long path, okay. So the water on this path is moving a little faster, water in this path is a little bit tortuous, so it moves, in a different form, right. So at this section, both these paths are bringing water, okay. So there is a contaminant solute that's sitting here, okay, and moving along this path, okay. There is nothing here, so there is a concentration gradient, right. So the molecule will diffuse out and go to this location, okay. But before this molecule can actually come back, okay, this flow path has actually moved a little bit, okay. So because it has moved, chances are now there is a clean or a less concentration coming in, and this molecule might diffuse right back in, okay. So there are two phenomena at play. One is the velocity in individual pores is different, okay, and there is diffusion happening, okay. The diffusion will diffuse the chemical out to another flow path, but that might get carried away faster or slower depending on what the velocity in that flow path is. So a dispersion, but we are not looking at the pores, right. We are only looking at what's happening on the average of the pores, okay. So when we look as an average, what's happening is molecules are kind of moving and getting mixed across different flow paths. The same thing can happen on this as well, like in this direction as well, and it can happen in this direction as well. But what's happening is diffusion is causing molecules to move from one flow path to another, and when they go, they are going on to a different flow, they're moving at a different rate. So there is diffusion and there is differential advection at the pore scale. But we can't see what's happening at the pore scale. We only see what's manifesting on a larger scale. And that larger scale, what we are seeing is that the solute has just got mixed. Okay. So hydrodynamic dispersion arises basically is a measure of mixing that's taking place in my aquifer because the water is moving at different flow rates in the individual paths. So it's a manifestation of that differential flow paths that we are not measuring. What we are measuring is an average velocity, okay. But not all flow paths are moving at that average velocity. Some are moving at faster rates, some are moving at slower rates. Okay? And when you add diffusion to it, what it creates is it causes the molecules to move at very different rates, which is tantamount to mixing, basically. Okay? If I take a coffee, and store it where I'm storing, I have the highest velocity, and right at the walls of my coffee cup, I have zero velocity, like a no-slip boundary condition. Okay? So there is a velocity gradient inside my coffee cup. So things are moving, the sugar is moving from where I'm storing out to where it, to the outer flow paths. It will not diffuse back that quickly. Okay? Eventually what I'll do is I'll end up mixing so that the concentration is same everywhere and there is no more transport. But if I just mix few times and you take a sip, right, the coffee will taste bitter. The first few sips will be bitter, and then as you keep going down, it gets better and better, right? Because it gets sweeter and sweeter. I don't know if sweeter is better, but it at least gets sweeter. Okay? So that's because there is incomplete mixing. Okay? You don't want that in a coffee. You definitely want it completely mixed because you want the coffee to taste uniform throughout. You should have the uniform coffee drinking experience as opposed to drinking bitter coffee and then sweet coffee. But if it were a porous media and you let it do whatever it wants to do, you will have incomplete mixing. So you will see mixing in certain direction to be a little longer than mixing in the other direction. Mixing is going to be more where the velocity is high, and the velocity is obviously much higher along the direction of the flow path. So you will see much more mixing in this direction than you would in this direction. Okay? Because the gradient in one direction is much higher than the gradient in the other direction. Right? We just saw from our calculation. But essentially, hydrodynamic mixing, or dispersion arises because we are not able to measure diffusion and advection at every flow path. If we could write an equation in every flow path, if we could track what's happening on every flow path, we really don't need to put dispersion in our model. All we have to do is put advection, diffusion, and the model will be correct. But we cannot measure at every flow path. What we can measure is an average velocity. Because it's average, I have to somehow account for the standard deviation term as well. Okay? Because if I say on an average, this class got 60% or 70%, it doesn't give me the complete information about this class. Okay? If I, on the other hand, say, well, I got 60%, but there were 3 who got 90s, and then 3 who got 10s, and the rest, So I'll know what is the range of variability that's happening. Okay? So the average linear velocity has averaged across the pores, but it has not characterized the variability that I can see in that direction. The same thing in a pipe, right? The maximum velocity is in the middle, zero velocities are in the end. So there is a range of variability that you can see. And what dispersion does is it gives that second moment, or it gives us that variability associated with the movement of solvent. Okay. If I knew everybody's grade, I don't need to calculate the mean and standard deviation because I know everything, all the information I need, so I don't really need dispersion. Okay. So the grade is your average. So, but I'm saying your grade is an average grade. Then I need to start talking about why I need that variability, like what is the range of variability that's in that class. So that's what dispersion does. Dispersion happens. It's not happening because a dispersion is a manifestation of our inability to measure at a scale where the phenomenon is taking place. If we were to measure at a scale where the phenomenon was taking place, we don't need that. Okay, but we're not measuring at the scale where the phenomenon is taking place. We're measuring at a scale where we're measuring on a much larger scale than where the phenomenon is taking place. So we have to somehow capture some additional detail, which is your dispersion. Okay. Generally speaking, the first two moments, that is the mean and the standard deviation, tells a lot. Like, of course, there are other things, right? There could be skewness, there could be kurtosis. It may be that the women in the class are doing much better than the men. That would be a skewed distribution. That would cause some skewness. Those kinds of things happen. Higher order moments can happen with this, and they are accounted for looking at dispersion in the x-axis, in the y-axis, and the z-axis, and there could be cross terms. Okay? The flow in the x-axis can cause mixing in the y-axis, or the flow in the y-axis can cause mixing in the x-axis. So, if you want to truly characterize dispersion, we have to look at the complete tensor description of dispersion, okay? Which is, what is the mixing caused by movement in this direction and diffusion taking place in that direction, or movement in this direction and diffusion taking place in this direction, movement in this direction and diffusion taking place in this direction. So, all that combined will give us that dispersion tensor. But getting those cross derivative terms or getting those types of measurements are extremely difficult. So, what we do is we make a very traditional civil engineering assumption, which is if you have done structures, you have made this assumption. When we get stresses, what do? We only calculate the principal stresses, right? Stresses along the x-axis, stresses along the y-axis, but there could be stresses caused by loading in x direction on y direction, so on and so forth. So a stress is a tensor, just like dispersion is a tensor, but we only take the principal stresses. And here also we take only the principal dispersion, the dispersion along the principal axes, and neglect all that cross derivative terms that can cause. So, what we are interested in is what is the dispersion caused in the x-axis due to flow in the x-axis? What is the dispersion caused along the y-axis because there is some flow component along that y-axis? And what is the dispersion along the z-axis due to flow caused by z-axis? In theory, the flow along x-axis can cause dispersion in y-axis or in z-axis. Those cross terms are neglected, and we just keep the principal modes of dispersion. Okay. How do we model dispersion? So, we somehow have to write a loading and a flux term associated with dispersion. Okay. So, if you want to do modeling, transport modeling, any phenomenon that you want to model, somehow you have to write a loading term or a flux term for it. If you can write a loading term or a flux term, you have your model basically. All you have to do is sum up all those loading terms, and your accumulation will be due to that loading terms. You just have to figure out where is the accumulation taking place, and your model is ready. Okay. So, if you have dispersion, how do we write loadings? Okay. Really, there is no good way to write it. So, what we do is we assume that it follows Fick's law. Okay. Fick's law strictly is for diffusion, it is not for dispersion. Okay. And the biggest difference between dispersion and diffusion is diffusion will happen even when there is no flow. For dispersion to happen, there has to be flow. Okay. If there is no flow, there is no dispersion. Okay. So, we come out and write the loading just like we write for Fick's law, and we say, but instead of putting a diffusion coefficient, we put a dispersion coefficient. Okay. And this dispersion coefficient depends on two things. It depends on your geology and depends on your flow characteristics. Okay. So, we go further and we say that our dispersion coefficient, or the coefficient of dispersion, is product of average linear velocity v, which we just calculated, and alpha, which is our dispersivity. So, the dispersivity can be thought of as a correction that we are doing for velocity to our average to account for the variability that we have not measured. Okay. Is Fick's law a good approximation? Okay. So that question has been the holy grail of groundwater hydrology for a very long period of time. Okay. What we know is at early times the dispersion behavior is not Fickian, okay, or doesn't follow Fick's law. Okay. But as time goes by, Fick's law becomes a reasonably good approximation. Okay. So at early times or at very short distances from your release or your solute, Fick's law is not valid. But if you were to measure a certain distance away, Fick's law gives you a reasonably good approximation. The reason for that is when the solute is moving, it is mixing, right? So it's encountering like small pores, large pores, and it's getting twisted and turned as it moves through different pores because it's trying to adjust itself to the different pore sizes. But once you have sufficiently twisted the molecule, it can pass through any pore. Okay. In other words, your molecule or your solute has to encounter a set of pores so that it can have certain amount. The mixing keeps on varying, but after a certain while, the molecule has bent out of shape, so to speak, and it can go into any pore, and there is no more mixing. Okay. So if I go to a very large scale, long distances or large times, Fick's law works, because in the Fick's law, my dispersion coefficient is a constant. Okay, it's not changing with anything else, because I have del C del T equals d del C over del x, like, you know. So that d is not part of that derivative. It's not changing with distance. We assume that the d is constant. Okay, but at some early times, the d is actually a function of x, because it's the amount of mixing that's taking place. Okay. So how do we get dispersivity? Again, dispersivity, just like hydraulic conductivity, is a figment of our imagination. Okay. It is just telling us what is the average extent of mixing that's taking place. Again, if you go to individual pores, the mixing is very different. Okay. What dispersion tells us is, on average, what is the amount of mixing that's taking place. So it's a measure of average mixing that's taking place in our aquifer. We do know that our aquifer is not completely mixed. Okay. So we don't have a whole lot of mixing, but there is a certain amount of mixing coming because the water is moving through tortuous paths, and each flow path has a different velocity. Okay. So how do we measure this in the field? So obviously it's an average, so there is no instrument that we can create that will measure the average, so we have to back it out somehow. And just like a pumping test, we do what's called a tracer study. What we do in a tracer study is we inject the tracer at one well, and then we try to measure tracer at other locations. Okay, that's in a column study we call it the breakthrough curve. Like, you know, so we inject the solute, we wait for the solute to break through at the end of the column. Initially, you will not see anything, goes up and then kind of flattens out and then falls back if you remove the solute. Right. Same approach can be used in a tracer study. So there are two types in which, or two ways in which we can do tracer studies. One's what's called as a force gradient experiment. What we do is we inject here and we pump here. Okay, so we are injecting tracer at a certain rate, and then we pump tracer at a certain rate. Okay, that's a force gradient experiment. Then we do what's called as a natural gradient experiment. In a natural gradient experiment, we inject the tracer here, and we let nature take its course, and then we sample at this well. Okay. So in a force gradient experiment, we are injecting here, we are pumping here. Okay. In a natural gradient experiment, we inject here, and we let the solute move under groundwater velocity, under mixing, whatever, and then we pull it out here. We just sample here. Which one's good? Which one's bad? Would you do a force gradient experiment or would you do a natural gradient experiment? How many are doing a force gradient experiment? Any takers? How many of you want to do a natural? One person there, one person there. Why do you want to do a force gradient experiment? It's faster. Okay. Somebody who wants to do a natural gradient experiment? Come on, nobody wants to do a natural gradient experiment? You guys are smart, okay? So it is certainly slow because groundwater is moving at 0.28 meters per day, so it will take a long time before it shows up at your well, okay? And also it will move in all directions, so which means you have to have multiple wells to recover all that solute that you have injected. Remember in the first class we wrote the code where we were injecting at a point and we got a plume, okay? So we need to have sufficient number of wells to pull out all that mass to get the recovery. So one way in which we do, when we do a tracer test, one thing that's important to us is if we inject 1 kilogram, eventually we want to recover that mass, okay? Unless the tracer is reactive and it's lost because of other reactions. We usually don't want to use a tracer that's reactive. We want to use a tracer that's non-reactive or conservative, as we call it. A typical tracer, what are some of the typical tracers that we can use to do tracer tests? Any non-reactive substance, so the halogens are your best bet. Chloride, fluoride, bromide. Fluoride unfortunately reacts with certain minerals, so chloride and bromide are really the best things to do. Sometimes we put SF6, okay, that is the sulfur and fluoride 6. It's a fairly good tracer that's used quite a bit in oil and gas industry, and we can use tritium. What's tritium? H1? H3 plus, okay, so that's tritium. Interesting fact about tritium is if you go to a groundwater well and measure tritium, okay, and if you take a water sample from a groundwater well and you measure tritium in it, that means that that well has water, the well has gotten water after 1950s. If you go to a well, if you go to a very deep well and if you actually sample water and measure tritium, chances are you will not find tritium. So if you see tritium in a well, that means there has been water, that well has been recharged with water post 1950. Okay. In groundwater age, that's a very young water, okay, because our waters are several millions of years old. Okay. It took millions of years to get groundwater to where it was. It takes no time to pull it out and use it. Okay, that's the downside. But if you have no other choice, you will pull it and use it, because what choice do you have, right? Okay. But if you measure tritium and you see tritium in your water, that means that well has been recharged at least after 1950. Okay. Why is that? Why do you think we look at tritium? Why is this happening? Yeah, tritium is radioactive. But why is that we measure tritium in shallower aquifers that have been recharged after 1950, and we don't measure it in deeper aquifers that have waters that are much older, that have not been recharged? World War? It's not you don't have to blame the World War for it. You can blame, yes, it is after World War. What happened after World War? There was a Cold War, okay. Russia and US started fighting, and they started making nuclear weapons, and they started testing nuclear weapons. Okay, so there was a lot of tritium put into the atmosphere because of the nuclear testing by Russia and U.S. Later on, China joined in, France joined in, and a bunch of other people. 1972, India joined in and said, we can't be left behind. We will get nuclear weapons, right? Because of that, we see, because there is so much tritium in the atmosphere, that we see water, recharged water. So we actually tracked tritium to see if there was recent recharge in some of these aquifers. And we usually call the water, if you find tritium, we call it the bomb water. Okay, so because it came out of nuclear testing. So tracer tests are one. Force gradient tracer tests are not really a good way to do tracer tests, because it actually alters the flow paths. Okay, so if I have a well, and I have a well, I'm injecting at this well, and I'm pulling out at this well, extracting at this well, the flows will all converge to that well. Okay, so essentially what you're doing is you're forcing the dispersion to be higher in this direction than in this direction. Okay, so you will overestimate what we call the longitudinal dispersivity, and you will underestimate what's called as the transverse dispersivity. If you do a natural gradient test, you actually put a well and you inject, and it starts to move, and you have to have multiple wells that will capture that plume. Okay? And you have to sample over multiple wells. Okay? The best, there have been like 2 or 3 very, very well designed natural gradient experiment tests done in the world, actually. So the very first test was done in 1980s, and this was done in Canada in Borden Aquifer. And Borden Aquifer has this Ottawa sands, what are called Ottawa sands, which are extremely homogeneous, or as homogeneous as you can get sands. Okay, really nice fine sands. You could actually buy them from places in the U.S. And this was done by University of Waterloo in conjunction with a few other folks, many other U.S. universities and USGS, and a bunch of people got together and did this test. And they had an old landfill in Ottawa, and they got the Canadian government to say, we're going to inject a tracer, we're going to inject benzene, we're going to inject toluene, nobody is around, nobody is going to be harmed, but we are going to learn so much about how these chemicals move in subsurface, because we really don't know how to do it. Okay? And we are going to do a natural gradient experiment as opposed to a force gradient experiment. So they injected all these chemicals, and as the chemical was moving, they were constructing wells, okay, and tracking what the monitoring was. So they said, okay, we tracked it here, it took about this 2 days, right? So we're going to go and build another well here, and then track the next plume. So literally they chased that plume and got a very, very detailed data set. You can actually buy this data set these days. There was another test that was done in the 90s, in the mid 90s, in Cape Cod, Massachusetts. Again, very, very fine sands. This is a coastal aquifer, so you had really good sands. And they did the very same type of test, which is a natural gradient test where they went and tracked the plume. Okay, Ottawa sand. Going back to Ottawa sand. Going back to going to the Borden Aquifer where they did the first test. What happened? Fairly homogeneous. They injected it. What there was a sand, there was a clay lens in between. So they injected it. They injected it this well, and there was a clay sitting here. So some of the plume went in this direction, some of the plume went in that direction. Okay, so it ended up forking out, even what they thought was a very, very homogeneous aquifer. So they had to go put a bunch of wells here and a bunch of wells here, and of course these two plumes at some point merge. So they had to put a bunch of wells all along, like, so millions of dollars were spent, but one of the finest experiments that has been done. It's very, very hard to replicate that type of experiment. What is usually done to calculate dispersion is we calibrate models. Okay? We say we don't know dispersion, but we know concentrations. Let's back out dispersion. Okay? That is the worst way to get dispersion because calibration is non-unique. The best way to get dispersion is to do a natural gradient test. Okay? Somewhere in between is a forced gradient test. Okay? So if you want to reliably look at, like, what is the reliability of your data, numerical methods or, like, using calibration would be the worst, would be like rated number 3. Natural gradient experiments would be rated number 1, and then the forced gradient experiments would probably be rated number 2. So in 1992, Gelhar, who was at MIT, published this paper, very famous paper, and actually you can go to Google and download this paper because a lot of people use it in their classes just like me, and they put it up on Google, so it's almost, you can get it. And this shows how longitudinal dispersivity varies with scale. The scale is where I injected to where I measured, the distance is the scale. Okay? And what we see is that there are fractured and porous rocks, okay, and the circles, the black circles are your tracer tests, okay, and these are your numerical, these are like force gradient, some just tracking contaminants using models. So they are looking at the best things are the tracer tests, as I said, and those are these dots, okay. What we typically see is that dispersivity keeps on increasing, and then starts to kind of taper off or increase very slowly at longer scales. Again, as I was talking before, it is the amount of mixing that's going on. So when the gradient is high, when the distance is low, you'll see quite a bit more mixing, right? Just right at the spoon of your coffee cup, there is a lot more mixing than at the walls of your coffee cup. Okay? So the molecules have encountered all kinds of heterogeneity before it hits that value, and that's what the scale is telling us. So there is a scale dependence. What we typically see is that dispersivity increases and then tends to go more flat. Okay, you will see a few outliers here and there. Those are because of the numerical. Some of those are just obtained from calibration. So not good data sets, but generally that's what you will see. So somebody said, okay, here's the data. It has got an x-axis and it's got a y-axis, right? So I can set an equation, or I can put a predictive equation and start using that equation. Okay? So they went and did a regression model and fed that equation, and that is also a very famous paper. And this is the equation that we typically use. Alpha L is your longitudinal dispersivity. It's 0.82 times log 10 L raised to the power of 2.466. So that scale has to be in meters for this equation to work. Okay. So there are about 100, I think 110 data points in that chart, and those are actually the best measured dispersion values in the entire world. This paper was published in '92. It's been about 16 years. We have added a few points along the way, but it hasn't changed much as far as the paper goes. So we still tend to use that equation. What about dispersion? So that is just telling you dispersion along the groundwater flow. What about dispersion in y-axis, and what about dispersion in z-axis? So dispersion along the groundwater flow is what's called as longitudinal dispersion, and dispersion normal to that flow is called transverse dispersion, and in the z direction that would also be transverse because it's normal to this x axis, but we tend to call it vertical dispersion just to separate it from this dispersion. Okay. What people have typically found is the dispersion is highest along the longitudinal dispersion are the highest values, which is to be expected, right? You're moving in that direction, so your mixing is going to be larger in that direction. What about this and what about this? Those are even difficult to estimate, because not only do you have to do a natural gradient test, you have to do wells that are nested if you want to get the z axis, because you're looking at mixing that's taking place between the wells. Okay. So, and then you have to have wells normal to the direction of groundwater flow to calculate what's happening in this direction. So, those tend to be a lot more difficult because your measurement errors sometimes become very high because you're measuring very low concentrations and they're not very accurate. So, as a rule of thumb, we generally estimate longitudinal dispersion from this graph or using that equation, and then we assume our transverse dispersion to be about 10 times, so 1/10 of that, and then our vertical dispersion to be about 1/100th of our longitudinal dispersion. There is really no basis for this. It is just a rule of thumb that is considered what is called as a standard engineering practice. So, we just do it because everybody has done it, and if everybody does it, we are okay doing it, right? So, but a lot of times at least it gives us a good start as to how dispersion is taking place. But there is nothing magical to that factor of 10 that we are using. Okay. So, that brings me almost close to our lecture. So that's how we model advection and dispersion. What's that? The diffusion coefficients, we just know the chemical, we get it from the literature. Okay, so if you go to that website that I had somewhere, it gives you the liquid diffusion coefficient and the air diffusion coefficient. And if you have a chemical for which it's not measured, there are molecular scale estimation schemes. You can look at for organics especially, you can look at the bonds and you can look at the structure of the molecules. So, there is something called QSARs, or the quantitative structure activity relationships, and you can use that to calculate what the diffusion coefficient is going to be. You can actually measure it in the field, in the lab, and the way you do it is you set up an experiment very similar to what Fix did. You create a membrane, you create a little cell, you inject the chemical on one reservoir, and then you have your porous media in between, and then you do nothing but you take samples over time and then back out from Fick's law. So, that's how you would do it, but those are a little bit difficult experiments to do because it's volatile, so it will start volatilizing and stuff. So, if you have a chemical that's very volatile, then you have to somehow control it by closing it, otherwise you will end up getting different concentrations because some of it is just being lost to the air. So yeah, it can be measured in the lab, and actually people have measured it in the lab, but it's not that easy. Okay. If you have inorganics, you don't worry about, there is still diffusion that takes place because it's just a concentration gradient. If you have nutrients, diffusion will take place. You have chloride, diffusion will take place. So, there is a diffusion coefficient associated with all of these chemicals. Vapor diffusion coefficients are only for chemicals that are volatile, that can exist in vapor phase. And then the soil diffusion coefficients, it depends on what the liquid and the gaseous diffusion coefficients are. So, for some chemicals that are non-volatile, the gaseous diffusion is 0, you are only left with liquid diffusion. There are some chemicals that are extremely volatile and very little soluble. We don't worry about them unless the MCLs are even lower than that. And that happens with things like DDT and stuff. Its relative affinity is much higher. It likes to be in organic phase, but if it doesn't get to be in organic phase, it likes to be in the water phase. So so we just look at the relative affinities. So what's that? Multiple compounds together. What happens when there are multiple compounds? Each one will diffuse, each one will disperse, but generally speaking, if you look at the diffusion coefficient and if you look at when there are multiple solutes, right, there is only so much space in the headspace, so if some of that is being taken by one solute, then it makes it even more difficult for the other solute to get in. So you will see sometimes what are called antagonistic effects, and sometimes you see synergistic effects. So you may have a molecule, and this molecule may like this molecule. So this molecule will diffuse out, and chemically this molecule will go and attack. Will go there because it likes this molecule. So now the diffusion of this molecule has been enhanced because there is this, and that's a synergistic effect. The opposite would be if there is this molecule and this molecule goes there and it doesn't like it, it will come back. So the diffusion can go down. So if you have multi-component mixtures, your diffusion compared to a single component mixture could be higher or lower depending on how they are reacting. If they are all non-inert, then we use something similar to the Dalton's law of partial pressure, and we say, they are not interacting with each other. It's like a mixture that stays. So each has a certain space that it will take. So diffusion doesn't affect as much for those types of chemicals, but certainly mass transfer, absorption, some of the processes that we want to talk tomorrow, multi-component mixtures behave very differently from single component mixtures. If they are reactive, if they are not reactive, their affinity goes down because there are 5 sites. If molecule A takes 3 sites, there are only 2 sites available for molecule B. Okay. So the molecule B will, on the other hand, there could be 5 sites, molecule A takes 5 sites, but molecule B can go and sit on molecule A, and maybe 2 of those molecules can sit on molecule A. So there is actually enhanced sorption. So sometimes there is cooperative sorption, sometimes there is competitive sorption that takes place. So when it comes to mass transfer and reactions, multi-component mixtures multi-component mixtures behave very differently or behave differently from single component mixtures. Diffusion, dispersion, they tend to behave very similarly. There could be some effects, but they're not that strong.
Each compound have a different diffusion coefficient.
Correct. Correct. Each one will have a different diffusion coefficient. Dispersion coefficient, we usually don't look at the molecule structure. We are saying hydrodynamics drives it. Okay, so the scale and the velocity of your aquifer is what drives that mixing, as opposed to the chemical characteristic. Diffusion, on the other hand, is random hitting of molecules. How the molecules will hit, and if they do hit, how far will they move, depends on the molecular structure. And to some extent, it depends on what else is there in that. What else is it hitting? If it hits another different molecule, that's very different. It may not move as far. So the presence of salts, presence of salts can change your diffusion characteristics. So the salinity can make a difference. It's a multi-component mixture, just not all organics. So your diffusion can change a little bit. Usually we don't have data for those kinds of things, so we do the best we can. We take what data we have and. Empirical formulas for diffusion. What empirical formula is there for diffusion? Dispersion empirical formulas are, I would rather that we go to the chart and pick a value. At least we know what the values look like. If you plot that equation that I gave, which is an empirical formula basically, that's an empirical formula. That's the Zhu and Eckstein formula, but there are many others that people have fit this. This data has been used quite a bit for fitting models of different types, and so I would rather go to this chart and pick depending on the scale. Let's say I have a source here, and my compliance point is 100 meters away, so I would go to 10 squared and say, okay, what is the range of dispersion that I'm seeing, and pick a value from that range rather than try to use an empirical formula that just goes through the curve, and I don't know how it goes through the curve.
This is especially for the groundwater.
Right.
But in surface water, there are number of controls.
Oh yeah, surface water is all empirical, okay? Because it's easy to measure things in surface water than it's to write theory. Groundwater is completely opposite. It's very difficult to measure things for us, but our theory. So we tend to rely a lot more on theory than we do on, empirical stuff. There's a lot of mixing formulas, based on wind speed, based on velocities, based on sediment bed. If you have, which one will you pick is the question. So if you have multiple formulas, it's always like, which one did you pick and why did you pick that? Would be what the reviewers will be asking you. So you better have a good justification for picking something. And typically, one approach would be to take 15 different empirical formulas, get estimates, then take a geometric mean. And that way you can say, I got a best estimate from all these formulas. So that's one way to do it. Streams are a little bit different from lakes. Lakes have their own formulas. Streams will have their own formulas.
But again, in my model, I have different parameters, means constant, different type of components. For each component, I can't use same empirical formula because it's varying. For each component, dispersion coefficient is varying.
Correct.
So that in what
The diffusion coefficient will vary. Why will the dispersion coefficient vary?
diffusion coefficient?
Right. So the confusion comes sometimes in surface water is in groundwater it's very clear what's diffusion, what's dispersion for us. Okay. In surface water, some people just use diffusion to mean dispersion because they use the word turbulent diffusion as opposed to molecular diffusion. So surface water gets a little confusing. So you're talking about turbulent diffusion as opposed to molecular diffusion. Yeah. So dispersion and turbulent diffusion are roughly similar. They're it's not turbulence here, but it's just mixing because of tortuosity, because of our sands. Our flow is not turbulent in groundwater, but in surface water, the turbulence can cause mixing. That's turbulent diffusion. And yeah, you have to model each solute movement differently because each solute will break through at a different time, and the reason it will break through at a different time is because it's got different characteristics. So
For each solute, I have to use different empirical formulas.
you don't have to use different empirical formula. If you pick an empirical formula, and that empirical formula depends on chemical structure of the solute, then you have to apply it separately for each solute. Okay. Mixing usually is not molecular dependent. Okay. Although in theory, how much it will get mixed, if I put a big cube of sugar and try to mix it, the mixing will be very different from when I put grains of sugar and try to mix it, right? So to some degree, the size of the molecule should play a role in mixing, right? But in groundwater systems, if the size is too big, it will not go through the pores. So what we assume is that most of the things that we are tracking are roughly of the same size, because if it's too big, it will get filtered out. Okay. In surface water, that may not always be the case. Okay. You could have fairly large molecules, fairly small molecules undergoing mixing, and so there could be some chemical dependencies on mixing in surface water systems. In groundwater systems, you don't see that because if it's a very large particle, it will just not move through, it will get filtered out. Okay. So, but you have to track each of if you want to track 5 components, you have to have an advection equation for all 5, a dispersion for all 5, mass transfer characteristics of all 5, the reactions for all 5, then put them together and you will get your overall mass balance. You have to have one mass balance for each, and then for water you have to write a mass balance on your own. Other questions? Hearing none, guess we can break. And
Tomorrow class will be from 2 to 4:30.
Class tomorrow, from tomorrow onwards, it's 2 to 4:30. So today it was 3 to 5. Tomorrow it's 2 to 4:30. So we are going back to our regular